Welcome to the Deep Dive. Today, we're really getting into the weeds on some core industrial tech. We're talking about pressure transmitters. Now, if you've ever wondered what makes things tick inside, say, a big chemical plant or even your local water treatment facility, pressure measurement is, well, it's absolutely critical. It keeps everything running safely and efficiently. So our mission today, using this really detailed source material we've gathered, is to break down the four main types: absolute, gauge, differential, and the newer multivariable ones. We want you to really get the differences, where they're used, why they're used, and, some of the tricky bits involved. This isn't just about definitions. It's about understanding the why behind the choice an engineer makes. Okay, let's unpack this whole field. It touches everything, really, from simple pipes right up to advanced semiconductor manufacturing.
Yeah, and it's so fundamental. Pressure is, one of those basic physical properties you have to control in almost any industrial process. Think about flow rates, vessel integrity, chemical reactions. Pressure measurement is usually involved somewhere. And the thing is, picking the wrong device, that can be a really costly mistake. They might look similar from the outside, maybe a metal box with some wires and pipes, but how they work, what they reference, it's fundamentally different. Getting it wrong could mean anything from, say, poor efficiency or a ruined batch of product to much more serious safety implications. So we really need to nail down these four types, focusing on their reference points, their zero, and what job they're actually built to do.
Okay, so the sources jump right into probably the biggest split first: absolute versus gauge pressure. Getting this difference seems like step one.
Absolutely. It's the foundational concept. It all comes down to, what are you measuring relative to? What's your zero point? For an absolute pressure transmitter, or APT, the zero point is fixed, it's unchanging, it's a perfect vacuum, 0 bar, 0 PSIA. Basically, as low as pressure can possibly go. And achieving that isn't trivial. Inside the APT, there's a sealed reference chamber, very carefully constructed, often with special welding, to hold a high vacuum essentially forever. Well, for the life of the device anyway. This means the measurement it gives is the total pressure, completely independent of whatever the air pressure is doing outside.
Right, so the APT reads the actual pressure, including the weight of the atmosphere pressing down on everything.
Exactly. So if you're at sea level, the atmosphere adds about 1 bar, 14.7 psi. If your process is at, say, 2 bar absolute, that's the total value. Now, the gauge pressure transmitter, the GPT, that's different.
Yeah, the GPT is kind of the standard one you see everywhere, right? It measures relative to the local atmospheric pressure.
Precisely. Whatever the air pressure is right then and there, and remember, that changes with weather. With altitude, that's the zero for a gauge transmitter. So if a GPT reads 2 bar, it means the pressure is 2 bar higher than the current atmospheric pressure. If the atmosphere is 1 bar, then the absolute pressure is actually 3 bar. And that gives us that basic formula. Absolute equals gauge plus atmospheric. Or, gauge equals absolute minus atmospheric. Simple math, but the implications are huge depending on the application.
Okay, and this is where it gets interesting. Like you said, why spend the extra money on an APT with that fancy vacuum chamber? Where is that absolutely necessary?
It's all about avoiding interference from those changing atmospheric conditions. Because the APT includes the atmospheric pressure in its reading, it doesn't care if a storm rolls in or if you're up a mountain. Its reading stays true to the absolute value. Think about maybe a food processing plant using vacuum sealing, or like you mentioned, semiconductor manufacturing. These often happen in carefully controlled vacuum chambers.
Right, you need to know the real vacuum level, not just how far below the outside air pressure you are.
Exactly. Or consider altitude.
Yeah.
If you have a process sensitive to boiling points, like vacuum distillation in a chemical plant, maybe high up in the mountains where air pressure is naturally lower.
Ah, okay. A gauge transmitter's reading would drift all over the place just because the weather changed. Even if the process vacuum was stable, that could mess things up badly.
Completely. It could ruin the separation process, affect product quality, or even create safety hazards if pressure differentials across vessel walls aren't measured accurately. You need that stable, absolute reference point.
You mentioned semiconductor manufacturing too. I assume that's another key area.
Oh, absolutely critical. Those processes require incredibly pure, stable vacuum environments. A gauge transmitter just isn't suitable because its reference point, the atmosphere, is positive pressure. It literally can't measure a true vacuum accurately relative to zero. So yeah, anytime your process involves vacuum, or anytime you cannot tolerate shifts caused by weather or altitude, you pretty much have to go with an absolute transmitter.
What about something like a sealed tank? You mentioned vessel integrity. If a tank is sealed, do the outside atmosphere still matter? Why would you need an APT there?
That's a really good point, and it catches people out. You think sealed system outside doesn't matter, but think about the stress on the tank walls. The total stress is the pressure inside pushing out minus the pressure outside pushing in. Engineering safety calculations for vessel design are almost always based on absolute pressure ratings to ensure they're safe, regardless of where they're installed, sea level or high altitude. Using an APT gives you that true internal pressure, allowing engineers to accurately assess the stress against the design limits, considering the external atmospheric push. It removes ambiguity.
Okay, that makes sense. It's about the differential stress across the wall ultimately. Now, APTs sound great, but the sources mention accuracy concerns. Besides temperature effects, which probably hit everything, what's unique to the APT?
The biggest vulnerability really is the integrity of that internal vacuum seal. It's designed to last decades, but if even a microscopic leak develops over time.
The vacuum reference starts to degrade.
Exactly. Air slowly leaks in, the reference pressure rises, and the transmitter starts to drift, reading lower than the actual absolute pressure. It's subtle, insidious drift. That's why manufacturing involves such high-precision techniques and rigorous testing. And then there's just general sensor drift over time, which affects all instruments, but it's particularly critical for an APT because that zero reference is supposed to be perfect and unchanging. Regular, careful calibration is key.
Okay, let's swing back to the gauge pressure transmitters, the GPTs. They have that atmospheric tube, but you said they're the workhorse. Why so common?
Well, mainly because they're simpler, they're generally less expensive, and for a vast number of applications, measuring relative to atmosphere is perfectly fine, even desirable. Think about measuring water pressure in a city pipeline, or the pressure in an open storage tank, or maybe air pressure in an HVAC system. You're usually interested in the pressure above atmospheric. Is there enough pressure? Is it too high? Using the ambient air as the 0 point makes installation and calibration much more straightforward. You don't need to worry about maintaining a perfect internal vacuum. It measures positive pressure above atmosphere, but it can also measure negative pressure, like a slight suction or vacuum relative to the outside air.
And you mentioned some GPTs can handle both. The source called it compound pressure.
Right. A compound gauge is specifically designed for processes that might swing between positive pressure and a slight vacuum relative to atmosphere. Maybe like a system that uses compressed air sometimes and pulls a slight vacuum at other times. A compound GPT covers that whole range around the atmospheric 0 point with one device.
So putting it all together for selecting between absolute and gauge, beyond the vacuum altitude rule, what else guides the choice?
You always have the standard checks. What's the pressure range needed? Is the material compatible with the fluid? What are the temperature limits? The basics. But then you get into things like the required output signal. For decades, the standard was the 4 to 20 milliamp analog signal.
Why 4 to 20? Why not 0 to 10 volts or something else? Seems a bit arbitrary.
It's actually quite clever. It's a current loop, which is much less prone to electrical noise interference over long cable runs compared to voltage signals, which is a big deal in industrial plants. And the 4 part is key. 4 milliamps represents the 0 point of the measurement range, and 20 milliamps is the full scale. If the signal drops below 4 milli, say to 0 or 2 milli,
the system knows something's wrong. Either the sensor failed or the wire broke. It's a live zero.
Exactly. It provides inherent fault detection. It's a really robust and reliable standard, although newer digital protocols are becoming more common, especially for more complex devices.
Okay, so the takeaway is absolute for vacuum, or when atmospheric changes can't be tolerated. Gauge for simpler, cost-effective measurement relative to ambient air.
That's the core trade-off, yeah. Balancing the process need against complexity and cost.
Yeah.
Now we changed gears quite a bit. We've been talking about measuring pressure at one point. Now we look at measuring the difference between 2 points. Enter the differential pressure transmitter, or DP transmitter.
Right, the DP transmitter. This feels like a different beast altogether. It's not just about measuring pressure anymore, is it? It's using pressure to figure out something else, like flow or level.
You've got it. The whole philosophy shifts. A DP transmitter has 2 ports, usually marked HP for high pressure and LP for low pressure. Its job is to measure the difference, the delta P between those 2 points. It then takes that pressure difference and converts it, usually into that same 420 MA signal. But now that signal represents flow rate, or liquid level, or maybe even filter blockage. So remember, gauge measures process versus atmosphere. DP measures process point A versus process point B. One gives you pressure, the other uses pressure difference to infer flow or level.
And the number one application is flow measurement, usually involving sticking something in the pipe, right?
Yes, the classic setup. You install a primary element in the pipe, Most often, it's an orifice plate, basically a plate with a precise hole in it. Could also be a venturi tube or a flow nozzle. The idea is simple. This element creates a restriction. Basic physics, Bernoulli's principle, tells us that when the fluid speeds up to get through that restriction, its pressure drops. The DP transmitter is connected with taps just before the restriction, that's the HP side, and just after it, the LP side. It measures that pressure drop.
And the bigger the pressure drop, the faster the fluid must be moving.
Exactly. The differential pressure measured is proportional to the square of the flow rate. It's a very well understood, very reliable technology. Works for liquids, gases, steam, works in huge pipes where maybe fancier flow meters are too expensive or impractical. It's incredibly versatile.
Okay, flow makes sense. What about using DP for level measurement? How does that work, especially in a tank that might be under pressure?
Right, this is common for closed or pressurized tanks. You connect the HP port to a tap at the very bottom of the tank. This port sees the pressure from the column of liquid plus any gas pressure in the space above the liquid. Then you connect the LP port to a tap at the top of the tank in the vapor space. This port only sees the gas pressure above the liquid, so when the transmitter calculates the difference, the gas pressures cancel out. What's left, the delta P, is just the pressure exerted by the height of the liquid column itself.
And if you know the liquid's density.
You can directly calculate the height, the level, from that pressure difference. It's clever.
But, okay, connecting these things up means running small pipes or tubes, impulse lines, from the process to the transmitter. And the sources really hammer home that these impulse lines can be a major pain point. You mentioned one source saying maintenance was like 80% of a tech's job.
Oh, that's not an exaggeration. In some older plants or with difficult fluids, those impulse lines are the Achilles heel. If you're measuring something cold, they can freeze. If it's steam, they can fill with condensate unevenly, causing errors. If the process fluid is dirty, sludgy, or prone to crystallizing,
They clog up.
they clog up. And if one line clogs more than the other, the delta P urine is garbage. It means constant maintenance, flushing the lines, blowing them out, maybe installing expensive heat tracing to keep them warm. It adds a lot of operational cost and potential for error.
Which leads directly to the solution, the remote seal. How does that fix the impulse line problem?
It's a really elegant engineering solution. Instead of running the process fluid all the way to the transmitter, you use a remote seal system. This consists of a diaphragm, usually metal, that's mounted directly onto the process connection, like a flange on the tank or pipe. This diaphragm seals off the process. It's connected to the actual DP transmitter body via a thin, flexible capillary tube. But this tube isn't filled with process fluid. It's filled with a stable, incompressible fill fluid, usually a specific type of oil like silicone oil. So the process pressure pushes on the diaphragm. That pressure is transmitted hydraulically through the fill fluid in the capillary tube directly to the pressure sensor inside the transmitter body.
Ah, so the nasty process fluid never actually touches the sensitive transmitter internals. No clogging, no freezing inside the instrument itself.
Exactly. It isolates the transmitter completely. It's essential for corrosive fluids, highly viscous stuff, slurries, anything that would gum up or damage the sensor or impulse lines. Also great for very high or very low process temperatures, keeping the transmitter electronics safe.
Seems like a magic bullet. Are there any downsides to using remote seals? Those capillaries can sometimes be quite long, right?
There are trade-offs, yes. While they solve the contamination issue, you introduce a couple of new factors. One is temperature effect on the fill fluid itself. If that capillary tube runs through areas with widely varying temperatures, the fill fluid can expand or contract slightly, which introduces a small error in the pressure transmission. Good systems have compensation, but it's a factor. The other thing is response time. Adding the diaphragm and the long column of fill fluid can slightly slow down how quickly the transmitter responds to rapid pressure changes. For most process control, it's negligible, but for very fast-acting safety systems, it might be a consideration. Modern designs have minimized this a lot, though.
Okay, sticking with DP for level, we have to talk about the mounting position. This is where it gets kind of counterintuitive how where you physically bolt the transmitter affects the electronic setup. Zero suppression and zero elevation.
Right, and this is fascinating because it shows how intertwined the physical installation and the electronic configuration are. You can't separate them. The geometry is part of the measurement. Think of it like zeroing out a kitchen scale. If it shows weight when empty, you hit tare. DP transmitters need a similar adjustment, but it's based on the hydrostatic pressure in the impulse lines due to mounting height.
Okay, let's start with zero suppression. When do you need that?
You need zero suppression when the transmitter is mounted higher than the bottom process tap on the tank. So imagine your tank connection is low down, but for convenience, you mount the transmitter on a platform 5 feet above that tap. Now, when the tank is totally empty, the liquid trapped in that vertical run of the HP impulse line from the tap up to the transmitter is actually pulling down due to gravity. It creates a slight vacuum, a negative pressure on the HP sensor diaphragm.
So the transmitter would read negative even with zero level.
Exactly. So you have to electronically tell the transmitter, ignore this negative offset.
Yeah.
Start your 4 milliamp output, your zero level reading. Only when the actual tank level starts rising above the bottom tap, you suppress that unwanted negative head pressure.
Makes sense. So zero elevation must be the opposite situation.
Precisely. Zero elevation is needed when the transmitter is mounted lower than the bottom tap. Say the tap is near ground level, but you have to mount the transmitter down in a pit or on a lower floor, maybe 5 feet below the tap. In this case, even when the tank itself is empty, that 5-foot vertical section of the HP impulse line is always full of liquid. This creates a constant positive hydrostatic pressure on the sensor. So the transmitter would read 5 feet of level even when the tank is empty. You have to electronically elevate the 0 point. You tell the transmitter, your true zero level reading, your 4 milliamps, should correspond to this already existing 5 feet of pressure head. Only start increasing the output above that.
Wow. Okay, so getting that elevation or suppression value wrong during setup could lead to completely wrong level readings overflows or thinking a tank is empty when it's not.
Absolutely critical. It underlines that point about installation vigilance. The smartest transmitter in the world will give you bad data if it's not configured correctly for its physical location relative to the measurement point.
Right. Okay, that covers DP pretty well. Now, let's move to the most modern category mentioned in the sources, the multivariable pressure transmitter, or MVPT. What makes this different from just a really good DP transmitter?
The MVPT is basically taking the next logical step. It integrates multiple sensors into one device. Typically, it measures differential pressure, delta, just like a DP transmitter, but also static pressure, which could be gauge or absolute depending on the model, and process temperature, usually via an RTD input. But the real kicker isn't just measuring these three things. It's that the MVPT has onboard processing power to calculate a fourth, highly accurate value in real time, most commonly compensated mass flow or sometimes energy flow, like BTU flow for steam. Think about the old way. You'd need a DP transmitter, a separate pressure transmitter, a separate temperature sensor, all wired back individually to a control system or a flow computer, which then did the calculation. The MVPT does it all in one box, right there in the field.
So a big saving on wiring, installation points, hardware.
Yeah.
That seems obvious. But the sources emphasize an accuracy improvement too. Why is measuring and calculating in one device more accurate than doing it with separate signals?
It comes down to synchronization and eliminating latency. When you have 3 separate devices sending signals, maybe 420 MNA, back to a central computer, those signals don't arrive at the exact same instant. There's always a slight delay or latency. If your process conditions, especially pressure and temperature in a gas or steam line, are fluctuating rapidly, the computer might be calculating flow using a DP reading from a fraction of a second ago, a pressure reading from now, and a temperature reading from somewhere in between. This timing mismatch introduces errors. The MVPT measures all 3 variables practically simultaneously within its own housing. The internal calculation uses perfectly synchronized inputs, leading to a much more accurate final result, especially under dynamic conditions.
And the main calculation it performs is mass flow, particularly for gases and steam. Why is mass flow the holy grail here rather than just volumetric flow from a standard DP setup?
Volumetric flow, like cubic feet per minute or gallons per minute, just tells you the volume passing by. That's often fine for liquids because liquid density doesn't change much with typical process pressure and temperature variations. But for gases and steam, their density is extremely sensitive to pressure and temperature. If the pressure goes up or the temperature goes down, the gas gets denser. The same volume now contains significantly more mass, more molecules. A simple DP transmitter only gives you volumetric flow. To get accurate mass flow, like pounds per hour or kilograms per second, which is often what you need for chemical reactions, energy calculations, or custody transfer billing, you must account for these density changes.
And the MVPT does that automatically using its built-in pressure and temperature sensors.
Exactly. It continuously measures DP, static pressure, and temperature. It uses internal algorithms, often based on industry standards like AGA or ISO equations, to calculate the fluid density in real time based on the measured P&T. It then combines this dynamic density value with the DP reading to calculate the true mass flow rate. This whole process is often called dynamic compensation.
I see. So it's constantly adjusting the calculation based on the actual current conditions. That sounds powerful. But you mentioned custody transfer, like selling natural gas. Isn't putting all your eggs in one basket, one device measuring three critical variables plus calculating the billable flow a bit risky? What about redundancy?
That's a very valid point, and it's a standard engineering consideration. For extremely critical safety systems, or sometimes even for high-value custody transfer, engineers might still opt for separate redundant sensors for P, T, and DP, feeding into redundant flow computers. It increases complexity and cost, but maximizes redundancy. However, for many applications, including a lot of utility steam monitoring, interplant gas transfer, or process efficiency tracking, the accuracy gains and installation savings of the MVPT outweigh the single point of failure risk, especially because modern MVPTs have very sophisticated self-diagnostics. And think about the financial impact of inaccuracy. Even a 1% error in measuring the mass flow of steam to a large turbine or natural gas to a furnace can translate into huge amounts of money over a year in wasted energy or incorrect billing. The MVPT's ability to dynamically compensate and improve accuracy often provides a very rapid payback.
You mentioned diagnostics and calculations. That implies these devices need more than just a simple 420 mA signal, right?
Oh, absolutely. To get all that information out, the DP, the static pressure, the temperature, the calculated mass flow, plus all the diagnostic status information, you need a digital communication protocol. This is where protocols like Foundation Field Bus or Profibus PA come in. They run on the same pair of wires that power the device, but they allow for two-way digital communication. This means the control system can not only receive all the process variables simultaneously, but it can also query the transmitter for detailed diagnostics, check its calibration status, even remotely configure parameters if needed. It's a much richer, more data-intensive connection compared to the single analog value from 420 LA.
So MVPTs are really tailored for those complex high-value applications.
Yeah.
Measuring steam, natural gas, maybe compressed air in large facilities where energy efficiency is key.
That's exactly where they shine. Custody transfer of gases, steam flow measurement for power generation or large industrial boilers, energy monitoring systems, allocation measurement in oil and gas, any place where accurately knowing the mass or energy content of a fluid is critical, especially when that fluid is compressible and its density varies. So, just to kind of wrap up the journey we've taken here, we started with the absolute basics, choosing your 0 point. Absolute pressure, using perfect vacuum, essential when you can't have atmospheric interference or you're measuring vacuum itself.
Right. Versus gauge pressure, using the local atmosphere as 0, which is simpler, cheaper, and fine for most everyday pressure measurements above ambient.
Then we shifted to measuring relationships with the differential pressure transmitter, using the pressure difference between 2 points to infer flow or level. Super versatile, but you have to manage those impulse lines carefully, often leading to remote seals. And remembering the critical importance of zero suppression or elevation based on mounting height.
And finally, we landed on the multivariable transmitter, the integrated powerhouse, measuring DP, static pressure, and temperature all in one, and performing real-time calculations, usually for highly accurate mass flow of gases or steam, using dynamic compensation and digital protocols.
It really shows an evolution, doesn't it? Each generation of technology kind of addresses the headaches or limitations of the previous one. The MVPT tackles the synchronization errors and wiring complexity of using 3 separate sensors. The remote seal tackles the unreliability of fluid-filled impulse lines.
So for you listening, the quick takeaway is vacuum or no atmospheric interference. It's absolute. Simple pressure relative to air. Use gauge. Measuring flow or level via pressure difference. Use differential. And think about seals and mounting. High accuracy mass flow for gas team. Use multivariable.
And that brings me back to that point about the DP transmitter mounting the zero suppression and elevation. It really struck me reading the material how fundamental that is. It proves that accuracy in these systems isn't just about buying the most expensive sensor with the best specs. The physical reality of the installation, the simple geometry of where you place the device relative to the measurement tabs is just as crucial. You have to get the physics of the setup right and configure the electronics to match. Even with all the smart electronics and digital communication, that basic principle holds. The human element of careful installation and correct configuration is still absolutely vital.
That really does leave us with a provocative thought, doesn't it? In these incredibly complex industrial systems we build, how do we balance the drive for ever smarter technology against the persistent need for fundamental, on-the-ground human vigilance and understanding of basic physical principles? Where's the real bottleneck to performance the tech or the application of it? Something for you to think about next time you see the intricate piping of an industrial plant. Consider the unseen world of pressure being measured, calculated, and controlled. That's it for this deep dive.